Example 4.7. Figure shows a long straight wire of a circular cross-section, radius is A, carrying steady current I. The current I is uniformly distributed across this cross-section. Calculate the magnetic field in the region where R is less than A and R is greater than A. Okay. A long wire, radius is A. This wire, its radius is A. It carries the current where it is uniformly distributed. What we have to do? We have to find the magnetic field in two regions. One is inside the wire and another is outside the wire. R is less than A and R is greater than A. Okay. Which formula? Here we have to use Ampere's law. Integral B dot dl equal to mu 0 into total current I enclosed. Okay, first we'll take the case 1. R is less than A. Now, this is the inside the wire. I will take inside small a, the dotted line. That is the circle I'm taking. This is inside the wire. A value is less than R. This is R and this is A inside the wire. First, we will write the formula for current density. What is current density? Current per area. I current is flowing across the wire. The area of the cross section is pi r square. Current I is flowing in pi a square, where a is radius. Now, I would like to find out the current in the small portion of radius A. What is the cross section area? Area of this portion is pi r square. A is this cross-sectional. Now I'm taking inside dotted one. That is radius of this circle is R. How much current is there? I current in pi a square. So how much current in pi r square? So current density gives current per unit area. Current per unit area is pi a square. How much current in pi r square? That's why current density multiplied by pi r square. That is the current enclosed. That is I into I divided by pi a square multiplied by pi r square. Pi get cancelled. I r square by a square. This much current is flowing. Now we'll apply Ampere circuit law. Integral B dot dl. dl means this circular portion. Radius is r. So circumference 2 pi r mu 0 into current enclosed is pi r square by a square. So magnetic field becomes mu 0 I divided by 2 pi a square into R. Now this implies magnetic field is proportional to radius R. Radius R increases linearly. Now we'll go for the second part. What is the magnetic field outside the wire? That is now R is this one. This is the cross section I'm taking. So clear, it is clear R value is greater than A. Current enclosed. When you are going outside, entire wire is passing through this. So entire current is flowing through the inner side. That is current enclosed equal to I. In B dot dl, B into 2 pi r equal to mu 0 into I. So B equal to mu 0 I by 2 pi r. B is inversely proportional to R. First case, B directly proportional. Outside, B inversely proportional. Now we'll plot the graph. That is magnetic field versus radius. In first case, inside, it is directly proportional. B and R directly proportional. Second case, that is outside, B proportional to 1 by R, that is inversely proportional.